Good evening, everybody, and thank you so much for inviting me for your meeting. I just heard about them before, and it's a pleasure to be here. I would like to share with you today some thoughts about lifelong learning AI at the edge. So when we talk about lifelong learning, it's kind of AI that will continue working, and at the edge, it's important that we can actually do that we can do it out of the cloud, that we can do it without lots of energy. And these two things look a little bit opposing to each other. So I would like actually to suggest ways how we can think about them together. And, you know, is the only AI at the edge that works so well. There are animals everywhere that manage to do that. So maybe we'll be able to build something, you know, not an animal, but something a little bit one step further from AI towards this direction. So where we are in AI today. So we're looking at AI today, and this great AI in the computer seems to be fantastic, you know, classification, game playing, chatting, capabilities, you know, beyond what we thought that we may be doing. At the same time, as we take AI to the environment, sometimes we cannot fully rely on it. So this is a little bit of a funny contradiction. And the way that I see it is if we talk about how we prepare AI. So since the 80s, we were talking about first wave AI. At least that's how they call it in DARPA, which are these rules and programs like the good old rule-based system and decision support systems from the 80s. And then we're talking about the second wave AI, where we're thinking now about neural networks, so deep learning. And the main difference is, while in the first one, we were writing the programs after talking lengthily with experts and trying to understand what they do. For the second one, we don't speak with the experts, we actually film them. So we're just seeing how they work, how they react, and we're trying to fit the weights of the neural network so that our network reacts similar ways. So we don't need to understand it, we need to mimic this behavior. So for example, if we're talking about supervised learning, so we take the network offline and we give demonstration of images and we classify them. So we learn how it's done on the side. And then at inferring time, we take images we've never seen before and we try to classify them towards the same classes. And the same occur with reinforcement learning or with non-supervised learning, that we try inferring time to behave in a similar way of what we learned before that the network was doing. So either way, if we work in first wave AI or in second wave AI, either way, we will be talking about AI that has to rely greatly on what it was taught in advance. So it will be based on the program that we gave it, or else it will be based on the data set that we trained the neural network. And the issue with working like this with AI is that if we look at this graph with time and performance during training time, we improve performances. And, you know, we used to see this great training curve. But in reality, as we get to inference time, if we are around what we learned, it's okay. But if we round some environment or some harsh condition that we didn't expect, we cannot really deal with that very well. And I think the point here is that this type of AI is the AI of we know it all in advance. You know, I'm an engineer, I'm so smart, I really know what you need in your life, and I'm going to give it to you. And the same happened with the chat, which is a generator rather than a classifier. And we see the chat, you know, lose grounding after some time, generating some toxic content. We don't have great success to align what it does with social norms, or we see that it's limited in a way of proposing new concepts or ideas because it's built on being really dependent on the data set. And people show great research how when you change the data set, you change what the chat does, and that's true. And, you know, on the other extreme, we have all these people talking about AGI, artificial general intelligence, and some people in government are getting so worried from AI, where the one we talk about now, it's really about, we know it all in advance, that's how we prepare it. So let's look at promises versus reality. This is something that is very good in AI. We always can do things in the next 5 years. Within 5 years, something will happen, like we'll be able to have a perfect self-driving car. And if you want to really fix it, we can think about solution. So the first solution that I want to suggest is the following. Maybe we just don't have enough data collection. So maybe what we need for a good and safe self-driving car is just to collect 20 more years of data, and with a few thousands more cars going around, perhaps millions, maybe it's just a matter of more experience to the data set. Another option is maybe it's not enough that we have this huge building of clouds. Maybe we need even larger factories. Maybe we need to take 1/3 of the land of the United States to build clouds, and then everything will be reliable and good. Or maybe we don't spend enough energy in AI, and it's not enough that it's now already comparable to pollution like air travel, but let's put more energy there, maybe that. So this is one way of thinking of how to do that. And another way of thinking about it is perhaps let's stop for a moment and rethink what we're doing. So, there is a great correspondence between organisms, that we can think about them as following programs. And it's not just a cliche. There is a reason perhaps to think about it, because if we think about organisms that are working like following a programs, then we can think about what they do and translate it to AI. Or perhaps biologists can ask us, can give us particular features of their biological program, and you can simulate it in AI and suggest what functional roles this type of features may be playing in the system. And because this thought has been going for a while, that organisms are following programs, and because the Turing machine model is such a common theory of computation, in the last 50 years, people were modeling cells and brains and bacteria and whatever you find in nature is some kind of Turing machine. What I want to suggest is that the Turing machine is insufficient to describe nature. And because of that, it also limits AI, and perhaps we want to think a little bit differently. So, all of us know that this is just to make sure that we are in the same line, and that we know what's the Turing machine. And the main component here is that we simulate these human calculators, this Turing time, or the lady sitting in the back of the bank offices of other financial offices and calculating matrices multiplication. So that what he suggests is that there is not a lot of creativity in doing that, but there is a loadable program, let's say a program that tells you how to multiply numbers, some scratch paper, and once you have this loadable program, you can put in any type, any size of matrices with whatever numbers and calculate it because you follow a program. And this has been a great advancement in the basic for computer science, because just the fact that there is one universal parts that allows to load any programs into that is in fact a proof of existence of general purpose computers. So this is a very basis of what we think of computers. So let's think about Turing animals. So Turing animals will be these animals that we load the program to them perhaps before they're born. So they have huge brain encoding to everything, even rare everything that can happen. And if the environment changes beyond what was encoded to them, they will not really survive to procreate. And the Turing AI will be that we must load or train the program first, or the neural network first, before we start inferring. And it will not learn from mistakes no matter what. That's kind of the loadable program in the most extreme way. And the way, if we look at it like that, then we'll say that the holy grail of AI is the adaptive intelligence. So this ability to break away from the need to load everything, to control everything, and to talk beyond pre-programs and expected environment, to have some kind of system that will give them a little bit more freedom, or what Turing used to call to have it less spoon-fed, so that they can actually try to get something, try something and get it going. So if you want to think of this type of strong computing, we can think, we need some adaptivity. And I have here a question for everybody. So for the ones of you who know, I have a question here. Who said electronic computers are intended to carry out any definite rules of thumb process, which could have been done by human operator working in a disciplined but unintelligent manner? Anybody knows who said it? You can unmute yourself. You cannot actually, Dennis will not allow us. Do we have a chat? Maybe you can put it in a chat. I don't see the chat. Dennis, tell me if anybody answers. Okay, I will not, I don't hear you. I think you're muted. That's okay. I'm not going to try more with the programming our Turing machine. So this is a quote by Turing that when he tries to explain why he tries to bring radon to work and try to introduce some other out of the computer capabilities of randomness, of changing environment. So if we think what kind of model maybe will allow us to describe adaptivity. So he described a model that actually allows to change or maybe include randomness, maybe something that has more continuous space. And the suggestion of that is perhaps the analog recurrent neural networks. And by that, I mean any kind of neural networks that has two properties and the rest doesn't matter much. Analog in the sense that the neurons are not discretized. So we can think about them ideally as some kind of continuum, even if it's, not real continuum. And they're recurrent in the way that it's not input after 5 steps output, but there is a way to zoom in, to think a little bit more inside of everything. So this is a suggestion to think about different type of a model of computation as a basis for computing. And if we're doing that, then let me move that, we can actually get a continuum of computational hierarchy in that. So if you ask what's the computational power of neural networks, we cannot get one answer. It depends on what we assume. And if we change one assumption, we're already going to a whole different domain. So if we are in the discrete world and we're deterministic and our weights are pre-programmed, then these neural networks will give us exactly Turing machines. And the center model here will be the Turing model. But if we change even one of these features, we just get out of there. So if we change from discrete values to something that is more physical, real values, or if we change from, let me close that so people will not be worried that I'm showing them to everybody. So if we're going from deterministic to anything that has real randomness or real asynchronicity between neurons, we're already getting off the domain. If we have, instead of pre-program, we allow to have systems that are evolved in a way that was not described by the Turing machine in a full way, but it requires some outside information, like lifelong learning. Or if instead of thinking about one model of a Turing machine, the Super-Turing model actually allows us to think of, let's say, an animal that in every point of time, if we look at it, it actually follows a program. It's true. But if we look at 2 different points of time, it follows a different program because the program is not the same anymore. So this process that has learning and advancing, or if you want to never learn anything, but you have some way to encode all future eventuality, which mean real weights, if we have something like that, never advancing, but have tons of information, or be able to just get more information and advance, either way, we just go from one word to another word. And in reality, we don't just have two classes, but we get infinite hierarchy. And the infinite hierarchy can be based on the amount of information that the system, that the network is using in order to update itself. And, or the amount of information that it had there in advance that can update, that can affect the computation. So as we get more information, or as we're able to use the information more successfully, we're going here across the continuum of the Super-Turing computational hierarchy, where it's at bottom, it's the Turing machine, that it doesn't get extra information and it cannot update. And at the top of it, there is this system that can either update itself really well from environment, or that it has all kind of extra knowledge that was put in it very, very smartly. So either way, we get this infinite hierarchy. So now, with that, we just want to make sure that Turing agrees with us. So Turing allows us that it's okay, that it's that when he talks about Turing machine, he was not talking about intelligence, and he's actually telling us that he actually believes that machine can be intelligent, which means that he wants to look for something else, and that's what he did in his last few years of life, but he didn't stay longer to actually go there. In 48, he's actually, after he lost his job in the physics lab in London, because he was trying to work on a higher faculties of the brain, he explained to us why we actually should work on it and not to be influenced by people that are upset by it. He gave us many type of reasons that people get really upset at his work on computing. And one of that, he calls the head in the sand, like these people that say we cannot allow such a disaster that the computer will take over the world, and if it takes over the world, it will kill us and enslave us. You know, these people you hear this a lot. I heard it a lot in the government. Whenever I was talking about more intelligent machine, immediately they thought that it's intelligent, so it's going to kill me. And I didn't understand why. I have a very intelligent son, and I don't think he wants to kill me. So I don't understand why the AI will want to do that. So whatever. And then he has many other objections. I like the Lady Lovelace's objection. It's true the current machine can only do what they're told, which doesn't mean that the future machine will only be able to do what they're told. So this is from Turing. So we get approval from Turing to go further. And with that, we're going to suggest a different type of intelligence. And this intelligence is that we can have only short training. And once we're fielding, we don't stop updating. So we can actually start being fielded, and as we need, and we see that something is not great, then we start to update, and maybe we'll have another failure and continue, and another failure and continue. So this is like a machine that doesn't separate training and working. It can actually continue update if it sees some issue. It doesn't have to repeat all the time and be what you call robotic type of machinery. Now, it has some very interesting feature. The first of them, if we are saying that it's okay to learn here, it means that we don't have to learn everything in advance. The reason that we have so much data set in advance that is considered to be forced is because the belief that we cannot update later. So we need to have everything in advance so that we can ready for everything. If we don't have, then we save the time and the money of collecting this huge data set. And most importantly, all this effort of training that takes so much energy. People always tell you that training takes energy. It's not correct. Training of huge data set takes huge energy, and small training over time takes small energy over time. So it's not the training that is the problem, it's the size of the data that it's a problem. So less exhaustive searching for training set, no huge energy update in advance. And the nice thing is that, you know, if you have this AI that is now off and we cannot use it and we have to start training it from the beginning, it's not very nice for us. And this one is hope to, you know, we update our machine, we update our robot, we update our drone. We don't have to start from the beginning. We kind of start updating what needs it to be updated. So that's the suggestion for the lifelong learning. And there's two solutions that I think are very immediate. And one of them, what's the problem? You train on what you have. When you see that you have an issue, train on what the issue is and continue. So what's the issue here? Let's say that you're training on task one. And here at that point, you know it very well. You see, you do it for 100%, and then you start training on another task. So you start knowing this other task very, very well, but you start forgetting the previous one. And the reason is not because you don't have enough capacity for your network to have 2 tasks or 100 tasks or 1,000 tasks at the same time. But the issue is with the form of continual computing, because after the first one, we rewrote over all the weights. Now we're using, when we have task 2, if we're using the network that we have as a bare network and we start updating all the weights so that we'll know best task 2, then we update something that already had information and we may lose it. So just to add as we go without preparing for that is not a very good idea. So the other idea is, okay, you work for some time. When you have something that you just cannot bear anymore because it's making many mistakes, you collect what you saw, you put it on the side. Now you take the original training and the old training and start relearn everything. So it actually works very well in the sense that your network now will do what you want. It has the old information, it has the new information, it will do. The only problem is if we have a lot of data that took us 3 months to train, and now we have another critical 5 minutes that we need to train on them, and we start doing it again and again, it will be very hard to work like that. And usually our network will be offline, trying to handle what's happened outside. So just very simple solution will not work. And that's why DARPA said, okay, fine, we'll take it over. And we try to think how we can think about that AI that actually allows us to advance. And the most 2 successful solutions that came from this group, so this group worked in these years. I was in DARPA from 2016, so I was there to suggest and initiate and manage the program for its first 3 years. And then I went back to the university, and whoever comes after me will have to handle the rest. And the most successful solution that we found in these 5 years were either bio-inspired replay mechanism or self-directed learning. And it's not by a coincidence that these 2 came from biology. We tried everything possible. We had groups and lots of money in many countries, and they tried all kinds of things. And the fact that, these 2 won is not surprise, afterthought. We put a lot of money in things that didn't succeed, but all kind of other suggestion. And I'll just show you a little bit how it works. So I explained to you the catastrophic forgetting, and this is called continual learning one task after the other one. Like here, we separate 0 and 1 is one task, and separating 2 to 3 is another task. And many researchers and many companies worked on some regularizers that were trying to push every task to another part of the network so that small part of the network will handle it and will be able to put more tasks. And that kind of works really well for some tasks. But when we wanted actually to take the information that you have and let's say compare now 8 to 5 and ask, I'm giving you 5 and 8, can you separate them? The network will not be able to do it at all, because every piece of the network can do one thing, either 4 against 5 or 8 against 9. So this is continual learning, that you learn one task after the other one, and there's some partial solution. But lifelong learning is not exactly just the issue of continual learning, because we want first to put knowledge together, as I showed here, but we also want it to be working in the wild, in the sense that there is streaming of inputs that we have to handle, and we need to have information forward transfer. Like if we learned something in the past, I want to use it now. And if I learned something now, I want to apply it to things that I did in the past so I can do them better. And I don't want to separate this idea, this is task and this is task, because then I'll be very limited in my behavior and very robotics. So we want just a little bit more. And so the notion of brain-inspired replay that was done with 2 very, very brilliant people, neuroscientists, actually, both of them, and now they're doing also AI. So just to explain what the idea that they suggested to do is, this is the original retrain. When we keep everything on the side, all the data is stored in the side so that I can put it together and retrain the system. The other idea is generate and replace. So instead of keeping everything, I'm keeping a generator, and it helps me to generate some information about what I had in the past, and then I can retrain or replay them and do the training. The reason that it sounds very good, it sounds like dreaming and generation. And, you know, in dreaming, we reconsolidate, so people like it. But the reality was very tough, because the generation that you get is usually limited in many ways. And the way that actually worked really well is, instead of having separate part for training and separate part for generating, you have it together. It's one network. And, you know, you can think about it as cortex and hippocampus, or whatever way you want. But the main notion is that you don't generate all the way to the input, all the many layers, but you just generate a little bit. And by generating a little bit means that you actually learn to generate abstractions. So you saw input in great details, and you cannot generate great details, you can generate abstractions. The letters will look like that, like really hard to understand from outside, but they will be sufficient for the network to be able to learn. And when doing that, instead of going all the way down when you train more, you just go a little bit down. So you didn't solve catastrophic forgetting. It's not fully solved yet, but you can handle many more tasks and kind of make it a little better. So this was one successful way for brain replay. And the other one that is also a way of thinking about offline. If you have time offline, what you can do, you can take the information that you saw, and let's say you just saw images, and you take these images and start asking yourself question, like, I can take this part out and say, well, what should have been here? So even that this didn't come as a labels, it actually tells me that there is a missing part, and I associate this piece to the rest of the picture. I can take the image that I have and decolorize it and try to check different type of colorization and think what looks reasonable to me, and start learning what kind of coloring makes sense. Or with the inference image, I can take a whole image and take different parts. Like here, I will learn that train station comes many times with the same image with a train. So it's not just the wheels or the colors, it's something that comes either. And this kind of association helps us to make, you know, fast searches. Like if I'm searching for the kettle and I see the refrigerator, I'll start walking towards this direction. So these two came as pretty successful. And today the situation is that it's not fully solved. This is a very hard problem, but it already start coming in many applications. Companies are already selling this type of AI that is doing to some degree some kind of lifelong going. And it's nice because you don't need to learn one class at a time. You can just walk around and, you know, whatever you see comes in. And you get individualization and privacy because you don't need everything to come together. But the interesting part that I want to say is, in order to get this lifelong learning, you really need two modes of training. Not training in the sense of training online, but the ability to update yourself. You need something that goes online so that immediately you will not do something that is dangerous or that annoys the user too much, that cannot wait until, you know, a week from now when there is time off. But you still need the offline time for more careful consolidation, for kind of more larger organization of what's happened. So you really need these two in practice in order to get some very good online capabilities. So now I want to talk about, so we talked about the notion, what is this lifelong learning and where it is now, which start coming in places. The thing that seem to be missing here, and the thing that scare many people is how can we do it at the edge? Because in reality is lifelong learning is most needed when it's far from the cloud, because you cannot bring it to the cloud and retrain and come back. If you're away, if you have your own machine and it has to work at least for some time, you want to have some kind of lifelong learning there. And how would you able to do that without this huge kind of learning? So before I'm going forward, I want to go back to the Super-Turing model. And we kind of left it on the side, but there is a reality here and a secret here. So the secret here is that the Super-Turing model actually help us in the design of lifelong learning. You know, the majority of ideas that we gather came from the mathematics. So I want to give you just one feature that will help us with edge computing. So I didn't kind of bring the one that helped us with lifelong learning too much, except for saying, you know, you change to learning and it's kind of equal to having lots of information because you start creating this information to yourself. But the other feature, if you have analog recurrent neural networks, and so this would be activation function and some, let's say, linear combination from the other neurons and the input and some local biases. And you don't need to assume lots of things about the, except for monotonicity or semi-monotonicity. So the issue is this: there is a way to truncate the information in the neural networks, and the truncation means that I truncate the weights and I truncate the values in the neurons after some number of bits. So I don't work with unbounded many bits of values because I don't have such good measurement devices anyway, and it will just create one big mess and will not be practical. So there is a practicality here that I can actually, if I calculate for like k time, then I need only the first k many bits and not even all the time. So I just need a little bit growing bits as I go. So we have something like some kind of temporal robustness, which tell us that they compute chaotic classes, but they also the process of learning and computing. So we never need to have everything in advance. We just need more information as we need to compute more. This is sufficient to bring a Super-Turing. So we can have just this process of getting more as we need. And if we actually go to the more details, what it actually tells us that there is a Super-Turing principle and of using resources. And it tells us that there can be adaptivity. So you use only as much resource as you need. And if you need, you use only as much, resources you need, you can get really very interesting capabilities. So I'll give you an example. I live in Amherst, and it's a little town. And, you know, wherever you live, it's not more than 3 miles from the university. And we don't know what it means, traffic or traffic jam. So when I go to the university, I think I need 2 bits of focus in order to go to the university. You know, there is nothing much that can happen except for a cat, you know, walking around. But then comes the winter and it becomes icy. And after I slid, I'm very careful and I hold the wheel like that, and I'm kind of focusing. I'm going very, very slowly in very, very small advancement and use all my resources for that. So in the amortized time, I'll have little concentration over the whole year, and I have more robustness in the winter because instead of traveling regularly with 8 bits or 16 bits, I'm putting 105 bits of focus in ice time. So I get some kind of robustness, sometimes of low energy, and it works very interestingly. So I want to kind of bring here just to wave just a few points, and I'll tell you what they are. First, I told you for lifelong learning that I need to have some cheap, reasonable way to learn during inference. This is my online part of the learning. The offline, you can do whatever you want, you know, whatever you know to do, do it. But for the online learning, how can I do it without stop the machine? How can I think and update and still continue the driving? Then I want to talk with you about energy-aware methods, which I think are very important to what we're doing. I'll talk a little bit about temporal awareness, and then I want to end with the Super-Turing tests or with the lifelong learning tests. So I think I have 15 minutes. Am I right, Dennis? Just kind of show me if I'm right.
Yeah, that's right.
Okay, perfect. Okay, and I take question as we go, if you have, and also at the end, so I'll try to finish 5 minutes before the end so that I can hear your points and your thoughts, because there are lots of thoughts here, not just questions. You know, it's a field when we all needs everybody's input. Okay, so I want to talk about learning online. And so the way we usually learn in neural networks now is the backpropagation. And the way we're thinking about it, there is an input, we compute what we get until we get the output for this input of what the network calculated. There is a label, and maybe there is an error. If there is no error, there is nothing to do. If there is error, which is usually the case, we start working backward and updating our weights. So if I had the image of a cat and I said that it's a dog, or I said that maybe some percentage is a cat, it tells me that it is a cat 100%, and it updates. And what I need is I need to close the network now, because I cannot get more inputs. You know, I have a back waves, I have a waves here that go, and I need local memory because I need to wait until the error comes, and I need to remember what I said so that I can update these weights that comes into me. So I need local memory, I need weights that go back. It's kind of making my network heavier, and I need to freeze the network to the outside. So I'm closing, I'm just putting a note, I'm not here, or I'll come back soon, and so that I can propagate the errors. So what we want to have something that actually can work as I'm working. And it means that I will want to have the input and the labels come both here from the input, so that as I propagate things, if I use error, if I use label, if I don't use label, I don't even need it, but I want to go forward. So as I compute, as I'm going in the computation, if needed, I also update. And if not needed, I continue with the computation. So in fact, I compute, and as I continue computing, maybe I'm updating here. And if I have, you know, input after input after input after input, it's not a problem because I'm updating my input. I'm still here because I'm computing if needed. I'm updating very fast and continue. And the next input can come and be computed already with the updated network, even that it didn't finish to update. And if it needs, it updates it a little bit more, and I'm going as a sequence. So I never need to close it. So what's the trick? The trick is the following, and I'll show you this algorithm, because I found out that when I said that this algorithm exists, people kind of think that it doesn't make sense, but it does make sense. Think about it for a second. You know, we used to have, you know, these images, and then the labels say the word dog or the word frog, or the 0001 or 010, something like this. So this is the name of my classes to the network. And the way that I'm used to do is I'm taking the input in regular backpropagation. I'm taking the input, let's say this picture of this cute dog, and I need to transform my weights need to transform the input all the way to the end. So at the end, the input says 100. Okay, so I took actually image that is very realistic and took it to some weird kind of labeling that I decided for some reason that 100 is a great way to describe my dogs. So here we think a little bit different. So what we do, I'm taking this label and I'm transferring it to the input space. Okay, so there are many ways to do it, and it does not matter so much. I need the same size of the input. I can take the 100 and put it many, many times after each other, or I can take some random image for all of them and add this. Anyway, I'm having the same inputs, and I'm taking a twin network. Twin network is a network that has the same structure in both sides. So here I'm putting my input, and here I'm putting my label after it's transferred to the same word. I'm comparing them, and if needed, I'm making little updates here, and I continue. So I'm making the local update, and then I continue with the values. It doesn't matter what update I did, I'm already off. So here, this is the input after whatever the transformation was done before I update it. And this is the label with the transformation was done before I update it. And if needed, if it's very large difference, I'm updating. If not, I continue. At some point, I stop updating. So I go all the way to the end. So if you think what it actually does to us is that if we had images, and many images, we kind of learn that they have the same type of labeling, we start clustering them together. So it's kind of way of making clustering of the data that comes together in the data set. And what it gives us very interesting features because we can pipeline, so we don't need to freeze our input. We have very simple calculation locally, and we can do it with chip with no memory because we don't need to remember what we said in the past. We actually have this value now. If needed, we update and we can forget about it as we transfer it forward. And we can add concepts on the go. So if you have classes, we can add more and more classes because it's a very large space. So it's perfect for on-device AI. And the reality of where it is today, we have a paper, we call it signal propagation. Hinton also suggested work a few months later, and he called it, I think, forward propagation. And for either work, it's not perfect. It's not as beautiful as back propagation, but it does very good for some time. If it start going for a long time, it start getting hard. We need the offline consolidation, but it works perfectly for what we need in the lifelong learning for online. So this is kind of a solution. And, you know, I will be happy to have more solutions. So this is what we run now in the lifelong learning for the online time. So this is one issue. Now I want to talk about energy-aware methods. And with the awareness of methods, it can be also temporal awareness, sensory awareness. And I'll tell you what I'm talking about. This is Terry Sejnowski. He's a neuroscientist, and Devder and Francesca. Devder is my student. Francesca is also my student, but she's from psychology. So she does her main PhD there and just kind of collaborate with us. So when we talk about swap-minded control, if you want to have small devices, you know, when we have today reinforcement learning, and they tell you that reinforcement learning, you know, provides superhuman capabilities, it's because reinforcement learning is faster in terms of time steps in many orders of magnitude than our neurons. So it works very well. And if you start working it slower, it fails. And because it works that fast, we can assume all kinds of things, that there is no delays, that immediately it reacts and stuff like that. So it works when we have very large computers that we can assume it's working very well, but not otherwise. So if you want to have a system that doesn't get input every 10 to the minus 5 seconds or something like that, but more like, you know, slow, then we're moving from the very high compute energy and high control energy, which is a jerk, to a different kind of computing. So the first one we suggested, and it's in a Devder will graduate soon, so he will be on the job market. So I'm happy to give his a picture from his job talk that will come soon. So we're working on a network. This is the part that works like regular on a quick network. But then we have a lazy network that controls the quick network that works slow. And there's a switch network. It's another agent, RL agent, that decides how to switch between them, but it works very slowly. Okay, so it's the slow one. And then there's a gate, which is working very slowly. So we have here some kind of a network that has fast and the slow, so that we have the sweet spot of energy and performance. And they have multi-objectives. Each of them have its own objectives, because this one is about having low energy, and this one, you know, there is kind of performance and low energy. And if we start working it on a different systems, and what we compare it, so we compare it, you know, this is a regular RL. This is a method that is called temporal, that tries to have input and then do a sequence of steps without looking at next input. So we try kind of to save from itself to look at input. And so what is important is the return. What is more important to me is the jerk. So what is the jerk? And also the energy and the number of decisions. So we are the gray. The regular RL is the blue, and the orange is a method that was used to try to work with the not to look all the time at inputs. So what is a jerk? If you have actually a drone, and this drone is now controlled based on this, it will have a jerk. And if the jerk is very low, it will use much less energy also on the hardware. So we have here slow and small energy for the calculation and low energy on the hardware. So it's in a different world. Usually this is much more important even than that. And we tried it on some things, where this kind of researching is never ending. So we tried it on a few things. I like the mountain car because regular reinforcement learning are kind of failing very easily and don't know what to do when we take information on. So when we go to the type of continuous control, I think this is the most interesting. We don't have like necessarily this amazing jerks as we see, but this is the regular RL, and the right one is our results. If you see, the RL finds something that is using unequally things, and I don't fully understand that. We don't fully understand why it works like that, why when we teach it to see temporal, like more to the future, it balances and give this low jerk and balances and low energy behavior. We don't fully understand why we get it. It's so far, this jerk is just what we see, and there is much more work needs to be done for that. So definitely also work on sequence learning. And in sequence learning, we kind of teach the network to update for sequences. So it's something that we give it, and again, it can get very low frequency network and still get the same reward. And I'll continue here to the end. This is just to say, this is a type of neural networks that its weights are changing over time, but the seed of them is fixed. So we're learning the seeds of the weight, and we're learning a function. And if we have static weights, they cannot change the output a lot. And with the temporal weights, with a very small network, we can update a lot. I'm just moving. Yeah, what we get here is in the static network, usually we need to train large network and then we can prune them if needed. With temporal weights, we can start with very small network and just grow up as needed. So we never need to go to very, very large network more than needed at the end. So I just want to finish with the Super-Turing test, because it's really lifelong learning test, and it's really kind of something that tells us about the power of the system. So many times we think in computer science on what is called the interactive paradigm, or a way that instead of input and then we wait to the output and then we remove all the memories and start again with the fresh machine that has no memory, we can think about having in our life unbounded, infinite amount of input and output, until we cannot give output anymore, and without removing anything. So if we can think of the function that we can calculate like that, and there are many, many functions. If we think that if the middle one is a Turing machine, we can calculate Aleph 0, kind of like integers, the first order of infinity. If we have the analog recurrent neural network, this is work with Jeremy Cabeza. Now he's a young professor, with either Super-Turing or lifelong learning, whatever we call it, we get more expressivity. So there's actually a large difference, not only in the efficiency or the computational power, but also in the set of what you are able to do. And I just kind of want to throw that towards the end, that, the Turing test is trying to have us compare between some of kind of human and a Turing control system, while the Super-Turing test should be harder. I see Daniel is raising his hand. I have 2 slides. Do you mind? I'll just kind of ending here. This is really the end, and I'll go back to this one for all of us thinking. This is just suggesting whatever we try to do, we don't know now how to go in a way that is more realizable. Beyond that, there seems to be something natural in this class of Super-Turing. And I just want to suggest for the end that perhaps in a few years, what we call AI will not be considered intelligence without lifelong learning or Super-Turing capabilities and having reasonable energy. And just to say, this is a new kind of work still. We still not many people doing that. And we need help with especially with the edge intelligent And thank you very much. And I'm ending on time, and I'll take question. And